All right, so we are officially in chapter 5. And as far as chapter 5 goes, we're going to be looking a lot at area. And so hopefully you were able to watch that 4.10 video because that is something that we're going to use a little bit, not so much in 5.1, but definitely in 5.2 today. And I also talked about in that video the idea that we are now sort of officially in that second half of content for Calc 1. Okay. And so if we sort of root ourselves in things that we know, we've talked about position, velocity, and acceleration. And I wonder before we move much further, if we could talk a little bit about the velocity graph, okay? And so there is one activity this week on Desmos that will sort of take you back to this idea of the derivative. But I'm wondering if you can tell me on a velocity graph, what do the y values represent? If you have a graph of v of t, what do the y values represent? Yeah, the units, we could potentially represent them as meters per second. And maybe on a more simplistic note, meters per second means that the y values on v of t are velocity, right? And we do measure them in like meters per second, feet per second, centimeters per second, miles per hour. Those are all ways that we can measure velocity. If I then asked you about the slope on v of t, what would you tell me that the slope of v of t tells us about? Yeah, exactly. So the slope on v of t represents excuse the Monday morning handwriting, acceleration. There we go. Okay, so slope on v of t represents acceleration. All right, so we have velocity, we have acceleration, and then in that Desmos activity that I had us take a look at, that approximating area, what did the area under the v of t graph represent? Right, so you looked at a few graphs, but what did that area under the velocity graph tell us about? No, it does not tell us about acceleration. It's a valid guess. But the answer somewhere in those first few slides. It is not about acceleration, no. So think about the ships, right? The ships in the first couple slides, they were asking you, all right, the ship is moving at a certain rate. And then when they looked at the graph, it turns out that the area under that velocity graph does actually talk about that distance, okay? Now this, my friends, was the big takeaway from this graph, from this exercise, all right? And so if that's something that you're like, ooh, I didn't get that from that activity, I would encourage you to kind of go back and look at it again. I think sometimes some of the slides are almost too straightforward that we're like, obviously this makes sense, but a lot of it is meant to tie into the other parts of the activity, right? So beyond just finding area, we also have to think about what does this area represent? And so as we're going through this unit, we're going to be looking a lot at area under a curve. And in particular, what we want to think about, especially if we're very like sort of application based in our brain, we want to really root ourselves in this idea that the area under the velocity graph actually represents distance. Okay. And so when we think about the relationship between velocity and acceleration, how do I get from the velocity graph to acceleration? Like what calculus notation or idea might I use there? Yeah, we might take that derivative, right? So v prime of t will give us the acceleration. But how about if we go from the velocity and we want to get back to the distance? What notation should we use for that?
V double prime t.
It is not the v double prime t, no.
Just V of t, right?
Nope, v of t is going to be the middle one.
S of t.
We're looking for the calculus notation though, the calculus notation. Now this is going to be really tricky because it seems like only 8 people watched that 4.10 video and we kind of need that to go on with today's lesson, okay? So yes, for those of you who maybe watched that or who have seen calculus before, the notation we are wanting to use here is this integral symbol, v of t. And when we go backwards, all right, when we go from velocity and we go back to distance, we are using this thing called the antiderivative or the integral, okay? And so that is where we are going to be starting today, all right? We're looking at this idea of the integral, where before we had been thinking a lot about this idea of the derivative. All right, so what's new? What we are focusing on today is precisely this idea of area underneath a velocity graph. All right, now this is that Desmos activity. All right, so that Desmos activity not just helps us sort of calculate things, but also that idea of like, what is it that we're trying to find? And then in the bigger picture, what we're going to be asking ourselves is this question right here. How do we find the area between a curve and the x-axis? All right. So how do we find the area between a curve and the x-axis? And this will be our focus question for chapter 5. Okay. So how do we find the area between a curve and an x-axis? That is going to be a question that we ask ourselves a lot, okay? And so last week, I had us look at the Desmos activity, all right? And so the concept behind that Desmos activity really was this idea that if we find the area under the velocity graph, it represents distance, okay? But it also talked a little bit about this, about the approximation and this idea of something called an LRAM or an RRAM or an MRAM. And I know that we summarized some of that in the discussion, and I'm wondering if we can put down a few sort of global ideas here. So when we look at LRAM versus RRAM, so let's leave the middle one out for a little bit. What is the difference between LRAM and RRAM?
Which corner of the rectangle touches the function?
Yeah, exactly. So when we're thinking about LRAM and RRAM, we have our left approximation and our right approximation, right? And all of these talk about where the rectangle touches the curve. Okay, where the rectangle touches the curve. And so on Desmos, you were able to kind of play around with things and say, let me just change how many rectangles I see. Let me see what happens to the picture if that happens. And I think one of them even allowed you to go ahead and change that to like a lot of rectangles, right? So not just thinking about here's 3 rectangles and here's 7 rectangles, but what happens if you had 1,000 rectangles, right? And I'm wondering if someone can sort of summarize what happened when you tried, say, 5 rectangles versus 1,000 rectangles. What was different about the picture?
You get higher accuracy. The rectangles match the curve better.
Exactly, right? And so that's one of the beautiful parts about something like Desmos is you don't need to sit and draw 1,000 rectangles because who has time for that, right? We don't even have time to have fun on weekends. So why would we want to sit and draw 1,000 rectangles? But just by typing in 1,000 on that slide, you can see that just as Sophia says here, you fill in the space more. And so more rectangles leads to a better approximation. Okay, and so that's something that we want to add here on the end, that more rectangles makes for more accurate approximation. Okay. So the more rectangles that we have, the better our approximation will be, like the more efficient, not efficient, but the more accurate our answer will be. Okay, so I hope that you did go ahead and try those different numbers and just kind of see that for yourself. Okay, but we also talked a little bit about this idea of when something might be an overestimate versus an underestimate. But I'm not sure how explicit that was in the activity. And so I want to take a moment and kind of think about how we know if something is an underestimate or an overestimate. Okay, so let's start with a picture. And let's say that we had some function. And I'm going to have this function as, let's say, something like this. All right, so maybe it's like part of an upside down parabola. And if I wanted to split the area of this curve and find that area, so I'm really saying how much space is here between the curve and the x-axis. And if I wanted to split this into, let's just start with 2 rectangles, all right? Let's say we had a space like that. We just have 2 rectangles. If I use a left approximation, and then I used a right approximation, which one would give me an overestimate? Okay, so if we think about this in this picture, RRAM will give an overestimate. All right, and so in a poor attempt to sort of, draw this visual, we've got maybe that pink rectangle there would be one right approximation. And then this other pink one would be the right approximation. And we can see that those pink rectangles definitely extend above the function, which means we're going to have too much area there. What about our left approximation? Will it give us an overestimate or an underestimate? Yeah, this is going to give us an underestimate, or something where it is too little. Okay, too little. And so that might look something like this, like those purple lines would represent that left rectangular approximation. Okay. Now, in general, though, this kind of function, what would you tell me about the slope of this part?
It's positive.
Yeah, that slope is going to be positive. Okay, so here is a really important pattern. When the slope of a function is positive. All right, so when the slope of a function is positive, then LRAM will always give an underestimate, and RRAM will always give an overestimate. All right, so for folks who are always like, but is this always going to be true? In this case, it turns out, yes, when we have a slope of a function that is positive, the left approximation will always be an underestimate, whereas the right approximation will always be an overestimate. All right, so things from the right will be too large, they'll be above the function, whereas things from the left will be underneath that function. Right.
So something like a parabola would both would be about equal, right? They'd be about the same, right?
Exactly, exactly. So it's important that we're looking at sort of certain regions right now, because this, you're right, maybe there's like sort of another half to this parabola. And in that case, it would balance out because like half of it would be an overestimate, but the other half would be an underestimate. Now, what do you think I should modify about this statement so that I could switch which one is the overestimate and which one is the underestimate?
Putting negative functions.
Exactly, exactly. Okay. So when the slope of a function is negative, and what does that look like when we draw it? Well, maybe that is something like this, right? The slope of that function certainly is negative. And if we were to sort of designate a starting and ending point, and for the purposes of this, we're just going to draw 2 rectangles, we might see that our left approximation is over the curve, whereas that right approximation would be under the curve. All right. And so we could say now that RRAM will give an underestimate, whereas LRAM will give an overestimate. So we've got our overestimate, we've got our underestimate, and as you folks said in the beginning, which is absolutely correct, when the slope of a function is negative, then our LRAM will be an overestimate, whereas the RRAM will be an underestimate. Now, some people like to memorize these things. For me, I think honestly, I just draw a picture. I just draw a quick picture and I'm like, oh, which one is it gonna be? And you're welcome to memorize this. But I think it would also be important to think about like, how does the picture tie into that explanation so that, you know, like 2 years from now, someone walks up to you on the street and is like, so tell me about this right approximation. Is it going to be an overestimate or underestimate? And you could be like, hold on, let me draw a quick picture and then I'll tell you. Okay. So as silly as that sounds, I think that idea of connecting to why we're learning things makes it a little bit easier to sort of sort that in our brains. Okay. But as we said at the beginning of class, the purpose of this section today, because we've done some of that conceptual thinking outside of class, is to really think about what the questions would look like and how do we calculate those, okay? And so we're going to take a look at a few examples here. And in particular, we're going to start with this idea of a runner. And so we have the speed of a runner. And we've measured it over the first 3 seconds of a race. Okay. So there might be longer periods of time to the race, but we're only looking at the first 3 seconds. And we've measured that speed every half a second. All right. So at 0 seconds, at a half second, 1 second, 1.5, 2, 2.5, and 3 seconds, we're saying, let's find out how fast she's moving at that particular time. Okay. And so the first thing I want us to do, because Desmos did some of this for us, is I want to go ahead and plot these points on the grid. Okay. So we have a table right here. All right, we have a T and V of T. And so it might behoove us to go ahead and label our axes here that is time and the y-axis is our velocity. All right. And let's go ahead and graph these points. So I'm going to go ahead and graph these points. I'm going to have one at 0, 0. I'm going to have one at 0.56, 1 and 10. 1.5 and 15, 2 and 18, 2.5 and 19, and 3 and 20. Okay. Now, I don't want us to connect the points because we don't always know what happens. Like these are just snapshots. So it's possible that it sort of went like this, but it's also possible that it went like this. Right? We don't really know exactly how they connect. These are just snapshots of like specific moments in time. But looking at this picture, before we find our LRAM and our RRAM, do you expect that the LRAM will give us an overestimate or an underestimate? Yeah, we think that LRAM is going to give us an underestimate, right? Now, underestimate of what? Like I have a velocity graph. I'm looking for area underneath this velocity graph. What is that area going to tell me? Exactly. Okay, so the area under this velocity curve will give us an measure of how far the runner went. Okay, so if I find the area under the curve from 0 to 1, all right, so whatever that area is, that area will tell me how far she ran in 1 second. Okay. What if I found this area, like the area from 0 to 2? What would that tell me? Yes, this only works for velocity. So we're still on the velocity graph and we're looking for the area underneath the curve from 0 to 2. Exactly. That's going to tell us how far she ran in 2 seconds. Okay. What if I found the whole area from 0 to 3, all of this area? What would that tell us? How far she went over 3 seconds. Okay. What if I just found this area? Just this middle clump. Very nice, very nice. Looking at just the part that I've shaded in, I'm looking to find how far she went between the first second and the second second. Okay, so depending on which group you choose, that's going to tell you sort of how far she traveled over that period of time. Okay, and so that's what we're finding. All right, so what we're going to find first in part B, it says find LRAM using 6 rectangles. All right, so what we're going to do here is we're going to go ahead and take our x-axis and we're going to say that the x-axis down here, all right, will be the base of the rectangles. Okay. And so if I choose this whole thing and I said this is 1 rectangle, the base of that rectangle would be 3. How big would the base of each rectangle be if I'm using 6 rectangles? 0.5. How did you get that? Yeah, so I agree. I agree that that base of each rectangle is 0.5. How did we get that? 3 divided by 6. Okay, so let's sort of write that down as a generalization here, that if I wanted to find the base of each rectangle, okay, that I would take, so I would take how long the whole interval is, okay? So in this case, my interval would be 3 minus 0. So 3 minus 0. And I want to take that length and I want to cut it, so divide, into 6 equal rectangles. And so I do a little bit of mental math. I get 3 over 6. And if we reduce, we've got 1/2. Okay. And so that means that the base of each rectangle that we're going to draw here is going to have a length of 1/2. And if we wanted to think about this in general, we could say that the base is going to equal b minus a over m. Now I just put those letters down there, but I'm wondering if you can tell me, based off of what we've used some of those letters for before, what do A and B stand for? Yeah, the A and B are our starting and our ending points. And so if we look at our table, we start at 0 seconds and we end at 3 seconds. And so we might even be able to say that this is our A and this is our B. All right, so we're starting at 0, we're ending at 3. So that's why we put 3 in for B, 0 in for A. And then the last number that we haven't really seen before, this little n down here, right? That's the same as our 6. That represents how many rectangles, Okay. Now, it's all fine and good to have the base of a rectangle, but what we also need to do if we want to find the area is we need to find the height of each rectangle. Right? In order to find the area, we need base times height. We have the base, so we need to find the height, okay? And so if I were to use this table here, and I said, what is the height of the first rectangle if I use left approximation? Okay, so the question is, what is the height of the first rectangle if I use left approximation?
Is it 0?
Yes, this is sort of a tricky question to ask you at 7:37 on a Monday morning, right?
That was sneaky.
But our first rectangle is going to be in this region right here. And the left corner of that is indeed at 0. All right, so the first rectangle is actually just like a flat line right on the x-axis. Okay, so this is the first rectangle. Let me go ahead and draw that in so we can kind of see this a little bit better. This would be my first rectangle. Now, what's the height of the second rectangle if I use left approximation? All right, what's the height of the second rectangle? Second one is going to be 6, so that would be like something like this. What's the height of the third rectangle? Good, 10. All right, height of the fourth rectangle looks to be about 15, right? All right, got 2 more rectangles left. One of them has a height of 18 and the other one has a height of 19. Okay, so let's think about what values we just listed off: 0, 6, 10, 15, 18, 19. Okay, so let's look at that table again while I say those numbers. The values that we're going to use are 0, 6, 10, 15, 18, and 19. Okay. How could I have found those values from the table without drawing a graph? Because I know some of you don't like to draw pictures. How would you find this if you didn't have to draw a picture? So length times width, yes, but I'm asking you, where are we getting these numbers? Where do we get the numbers 0, 6, 10, 15, 18, and 19? Okay, so yeah, they're on my table, but did I use all of the values on the table? Okay, I did not use all of the values on the table, right? And in particular, to find the left approximation, which values did I use? I used the y values. Did I use every single y value in my table? Okay, let's see those values again. 0, then we said 6, then we said 10, then we said 15, then we said 18, then we said 19. We did not say 20. Okay. So one pattern that might be useful for us is if we have a table and we're trying to find the left approximation, we're going to use all of the values in the y values except for the last one. Why don't we use that last value? Because it's one thing for me to tell you, don't use that last one, but like, why? Yeah, let's look at this graph, right? If I wanted to use this y value, and that was the left-hand side of a rectangle, I would actually be going to find how far she ran in the first 3.5 seconds. I don't want the first 3.5, I only want the first 3. Okay. And so a lot of times when people say left approximation, you use everything except for that last one. What they're trying to tell you is if you drew a picture, the first values would give you each of the heights of those rectangles. But we don't need the last one because that would give you the value of the next rectangle over, and that's not in our interval. Okay. And so if I asked us to find the area of 0, 6, 10, 15, 18, 19, if I asked us to find the area of all of these rectangles, okay, we could write it one of two ways. We could say, find the area of this one, find the area of the second one, the third one, the fourth one, the fifth one, the sixth one, right? We have 6 rectangles. I'm going to find each area, and then I'm going to add them all up together. Okay. And so if I wanted to write that out, that might look something like this. 1/2 times 0. That's that first rectangle, the one that was a trick question on a Monday morning, plus 1/2 times 6, plus 1/2 times 10, plus 1/2 times 15. Anybody else's hand tired yet? Plus 1/2 times 18, plus 1/2 times 19. That would find us the area altogether. That's a lot of writing though. What would be a more efficient way of writing this? Like if I didn't want to sit and write out every single rectangle and its area, what would be a more efficient way of writing that? All right, so I like that we see this 1/2, right? And if we look, every single rectangle has the same exact base. And so, like Vince suggests, let's go ahead and factor out that 1/2. Okay, since every single one of those has a 1/2, we're going to go ahead and factor that out. Now, I know I have these y values, 0, 6, 10, 15, 18, 19. How could I represent these y values in general? Like without using a number, we could say that they are velocity values, right? 6, what's another way to write 6? Well, maybe I could say that is going to be v of 0.5, right? What would be another way of writing 18? V of 2, good. Right? And I could say this 0, another way of writing that might be v of 0. And in fact, I could say every one of these y values are just the velocity at some given t value. All right. So another way to, instead of saying 0, 6, 10, 15, 18, 19, I could say v of 0, v of 0.5, v of 1, v of 1.5, v of 2, v of 2.5. And so one of the things that we typically do is we'll actually go ahead and just write, instead of giving specific y values, we'll actually write this as our function notation. Okay. And so this, in general, this, I think, is sort of the very long way of writing it. This is actually a more efficient way. But what also makes it really efficient is from what we've written down here, we can actually generalize a formula. Okay, and so the formula at the end of the day is what we really want to be thinking about, what we're plugging things into. Okay, and so here's what I mean by that. We're going to go ahead and add an extra page, and we will do part C on the extra page. But in general, right, what makes things most efficient here, and by efficient, I don't mean it's the least amount of writing per se. By efficient, I mean we can use it for a lot of different scenarios. Okay, and so here's where I think sometimes students are like, why wouldn't you just turn this all into numbers and then just multiply and get a number, right? That's all fine and good, except if all you have is a number, it might be a lot harder to remember where those numbers came from, right? And when you're trying to apply it to a different problem, then it becomes a lot more difficult, right? And so what we're doing here is not saying this is the shortest way to write it, but we're saying this is a way that we can use for all kinds of scenarios, all right? And so in general, when we think about the area, let's actually say our left approximation. Anytime we think about our approximation, we're thinking that we're going to take base times height for each rectangle. And then we add together. Right? That's one way of thinking about that. In our case, because we've chosen very specifically, here's what turns out to be true. the base of our rectangles is going to be a common factor in every single one. We've divided these into equal rectangles. And so 1/2 or whatever that base happens to be will be in every single term. And so we're going to bring the base out to the front. Okay. And so what we'll have is the base times the first height plus the second height plus height of the second to last one. Actually, let me say that a little bit better. Sorry. It's going to be the height of the last rectangle. All right, so we're going to say, we're going to do that 1/2. We're going to pull that out to the front, just like we did with that. Sorry, we're going to take that base. We're going to pull that out to the front, just like we did with the 1/2. And then all that's left on the inside is the heights that we have to add together. And we're going to go ahead and use this piece here as well. So instead of saying base, we're going to do b minus a over n. And that will be a formula that you can use every single time we have any sort of approximation. Okay. So instead of base, I'm going to write b minus a over n. All right. And instead of height, I'm going to use function notation. All right, we're going to say f because we don't always know that it's velocity, but whatever our function is, we're going to plug in the very first y value. Okay, this is for the left approximation. So we start with the first one. The next one will be f of x sub 1. Let's skip a few. We're going to stop at f of x sub n minus 1. Okay. So I'm sneaking some notation in here on purpose. So I think it's important as we move forward in our calculus journey, not only is it fine with numbers, but that we can take a look at equations and still make that connection between the equations and the patterns that we've seen. Okay. As far as finding the area, we could throw that into a calculator. All would be fine and good, but we'll just leave that here for right now because the purpose of this is not necessarily to find an exact value, but the purpose of this is actually to set up that structure. Okay. And so what I'm actually curious about here is we've had this discussion about left approximation. How do we modify that to find the right approximation for 6 rectangles? And so here's what I'd like us to do. We have this equation right here. That equation will help us find the left approximation. How do we modify that equation to give us a right approximation?
Is it the f of x base 1 to f of x n plus 1 instead of minus 1?
Ooh, close. Let's get to that one in a moment. Let's maybe start with this one right
Oh, sorry.
in the black. That's fine. So let's start with something with a few more numbers, but you're on the right track. How do we modify this so that we can get a right approximation? Do we think we keep the 1/2 the same?
Yes.
Yeah, that 1/2 is going to stay the same.
V of we need to start from V of 1/2 and
Good.
finish with a 20. I mean, with a 3.
Good. So we're going to start at V of 0.5 and we're going to go all the way until we don't need the 0 height, but we need the 20, and that is our V of 3. Very nice, very nice. Okay, so let's go ahead and actually put that in the diagram though, okay? And so this RRAM situation, what would it look like, right? How did we get these Y values? Well, if I have this as my first base, the right-hand side of that is gonna be over here. So now the height of the first rectangle, if I use right approximation, is 6, okay? What's the height of the second one? Well, it's going to be 10. The third one will be 15. The fourth one will be 18. The fifth one will be 19. And the sixth one will be 20. All right. And so from our table, we're using all the Y values except the first one. Okay. And why are we doing that? Because when we sit down and try and draw it, if we want to come from the right-hand side, we don't need that first Y value, right? The right-hand side of 0 and 0.5 is 0.5. We're going to use that as the height of our first rectangle. And so if we were to also generalize this formula, right, how would we modify that? I think we were headed in the right direction. Oh, I'm missing a letter there. We can still say B minus A over N. We wouldn't start with f of x sub 0. We would actually start with f of x sub 1. The next one would be f of x sub 2. Plus, how would we represent the last one?
X of the last one, not N minus 1.
Okay, so let's see. If I think about this, I started with f of x plus, or f of x sub 0, and it became f of x sub 1. What did I do to that subscript? Like, how do I get from 0 to 1? You add 1, okay. So if I go with f of x sub 1, how do I get to f of x sub 2? I add 1. Okay, so now I have this subscript of n minus 1. When I add 1 to that, what do I get? I just get the n, okay? And so this last one is not going to be f of x sub n plus 1. It's just going to be n because the last one here before it was n minus 1. Okay, if you had f of x sub n plus 1, you would actually be looking at like the 7th rectangle or whatever is out here, right? Because n is 6. So we want to be getting to that last rectangle, not the one after that, okay? So I know this notation can be a little tricky, but I think for this is a really, like if you understand how to modify that equation, that's a really good place, like the one in the black marker, okay? So if you can modify this, that's a good place to be. if you feel ready to modify the notation, the one in the blue here, that is like extra bonus, like that's good, okay? We wanna be making sure we're all able to work here. And then for those of us that are ready, we wanna start to make that connection between the other ones as well, okay? But I want to pause here for a moment. I know Monday mornings are always a little bit hard. What kind of questions are coming up for folks right now, if any? And it's okay if we don't have questions yet, but I'm wondering what questions we might have so far.
Why it's important to learn it?
Good, great question. So sometimes we're going to find in a little bit that we can find things that are exact area. And so we'll find some techniques for finding exact area. But there's actually, as amazing as technology is these days, there are limitations to things that we can do algebraically, like with all the equations and stuff. And so sometimes in order to, like if we're trying to find out the area under some curve, like it's easier for us to measure the velocity of something, right? So let's say something is traveling like a bazillion miles. That might be really hard for us to measure, but if we can measure how fast something is moving, like say a space shuttle, how fast that's moving, and we get markers in time for how fast it is going, we can actually say with pretty good accuracy, depending on how many rectangles we draw, how far that space shuttle traveled. On the flip side, we might have something that's moving like very, very small distances. And so again, it might be really hard to measure really small distances. And so since we're learning about approximating, if we can measure how quickly that thing is moving at any given time, it might actually be easier to measure that and then unpack it using this idea of area to find out how far that thing went or traveled in that period of time. All right. But this also could be extended to if you ever take a, what does the area underneath a position and acceleration graph represent? That's actually a really good question. So I'm wondering if you can actually tell me based off of what we wrote here. So if I have velocity and I go backwards, I find the area under the curve, that gives me position. What do you think if you take the acceleration curve and you find the area under the acceleration curve? What do you think you'll get information about? Yeah, you would actually find out about velocity, right? And so maybe there's a situation where measuring velocity is much, or measuring acceleration is much easier. You measure the acceleration, you plot your data, you find the area, you're going to get velocity. Okay, so sometimes it's all about like what's easier to measure. And if we can measure certain things better, and then we can mathematically unpack that, then we can find what we actually wanted to find. Okay. All right, great question, Luca. Like, why are we getting these values? N minus 1 is 5. Okay, and so what we're saying is that t, these x values, actually have notation with them as well, meaning that this is really x sub 0. This is x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, x sub 6. So it's not that this is x sub 1 because it's 1. It's x sub 1 just means this x value. If I said x sub 5, I would mean this x value, like the 5th x value. And sometimes it depends on the notation. Some people do like to start at 1. and that would be okay. You would just have to make sure everything sort of lines up. But a lot of times this first one is sort of like the X or not the X, the Y intercept. And because it's the Y intercept, we just call it our starting point or X sub 0. So especially in a lot of applications, we'll use X sub 0 as like the starting thing. So then everything is sort of one less than what you think it should be. Like this is the second X value, but we call it X sub 1. Okay. All right. I do want to take a look at part D. And then after we take a look at part D, yes, exactly. When you're looking at computer science, you want to start at 0, and it goes back to that idea of a y-intercept. Exactly. All right, so let's take a look at part D before we take a break. All right, so part D for the same graph, and let me go ahead and plot these values again. We had 0, we had 6, 10, 15, 18, 19, and 20. All right, and remember this is our time and this was our velocity. All right. And so in this case, I want to use only 3 rectangles. Okay, so I'm only going to be drawing 3 rectangles. And so I'm wondering if you can tell me how long the base of each rectangle is if I only have 3 of them. All right, I see 1. Do we agree? Do we disagree? Yeah. And so one thing that we might start to write out here is the base of each rectangle. Now, I see people saying 1. Let's use that formula and confirm whether or not their answers are true. So the length of the base we said was b minus a over n. What's our b? What's our a? What's our n in this case? Good, we've got b is 3 minus a is 0. And this time we're using 3 for our n because we only have 3 rectangles. And so 3 minus 0 is 3. 3 divided by 3 gives us 1. And so you folks are absolutely correct. All right. Now that means that if I were to sketch here, that I would maybe want to divide here, divide here. All right, so I'm taking this whole bottom piece and I'm cutting it into 3 equal pieces, right? And each one of those pieces has a length of 1. Now, I'm wondering if you can tell me about the height. And before you start giving numbers, can you write the height using function notation? Okay, so instead of saying like 10, I would want you to say f of 1. All right, so what are the heights for each of the 3 rectangles that we have here? We want to make sure that we're using X values inside the parentheses, right? So something more along the lines of what Jeremy has here, that like, yeah, those are X values in there, right? So we don't want to put the Y values in there. We want to put the X values in there. No worries, no worries. Okay, so if I were to look at this first rectangle, oops, if I were to look at this first rectangle here, where is the middle? And when I say where, I mean, what is the x value of the middle of this rectangle? 0.5. Okay, so this M right here stands for the midpoint. And so I don't want to use the
Can't
left-hand
hear
side.
you. I don't know why.
What's that? I'm sorry, I didn't hear what you said. Oh, okay. Well, is the sound coming through okay? Yeah, okay. All right, let's try this again. So if we take a look at this rectangle, right? If we use f of 0, what would that be giving us? LRAM or RRAM? Yeah, if I used f of 0, that would be LRAM. What if I used f of 1? What would I have? I would be using RRAM. So what should I use if I want MRAM? I have to use the height of the X value in the middle. Okay, yeah. So let's pick a new color here. All right, so we're actually going to be using this F of 0.5 will give us the height, and maybe to stay consistent, let me say V of 0.5. That will give me the height of the first rectangle using MRAM. What would I call the height of the second rectangle? Good. We're going to go again to our second rectangle. We don't want to use f of 1 because that would mean we were doing left approximation. We don't want to use f of 2 because that would be right approximation. Rather, we want to use f of 1.5 because that will give us the middle. All right. And for the last one, we'll use f of 2.5. And that again will be the middle of what we have. So if we write those down, we'll have V of 0.5, V of 1.5, V of 2.5. So if I wanted to write my area formula for MRAM, I would maybe say 1, because that's the base, times V of 0.5 plus V of 1.5 plus V of 2.5. And whatever numbers come out when I plug in the y values from the function, that will give me my MRAM. Okay. So we've taken a look at like MRAM, LRAM, and RRAM and how you figure out like what that formula is. My recommendation would be this. The students who have tried to sort of memorize formulas, usually it all falls apart on them. But the students who take the time to really connect where their values are coming from and how they can find those in different situations, those students tend to find more success on these questions. Okay, so I would encourage you, memorizing is sort of like one level of understanding, but being able to connect between different representations, that often makes things a lot stickier in our brains. Okay. So before we go on break, I just want to say one thing about this trapezoidal approximation, and that is that if you, this is something you can explore on your own time. It's another way of thinking about approximations in a like how else people said, oh, I would like to not get an exact value, but I would like to approximate something. All right. But this is only if you wish. All right, I will not test you on this content for the trapezoidal, but I will be asking you about the rectangular ones. Okay. So let's go ahead and we're gonna stop here for a break. So let me go ahead and pause that recording. All right, folks, I hope you had a good break. We are gonna go ahead and finish up one more example on here, which will hopefully sort of either show us where we might still have some questions, which is very beneficial, or might show us where we actually do have some sort of aha moment, okay? So no matter the result, I think it's important to kind of see things at least more than one time, just to kind of get an idea of where we are and how we might be able to either craft some questions or really be able to make sure we understand things thoroughly. Okay, so let's take a look at this second example right here. And so this is something that we haven't seen too much of yet, all right? But we have seen some of this, and in particular, this squiggly symbol here and the dx at the end, those two together are called your integral symbol, okay? Can't have one without the other. You have to have both. The inside part, in this case, x squared, that is our function that we are integrating, or we also call that our integrand, okay? And so what we're going to do is we're actually going to start by drawing the function x squared on this graph right here, okay? And so we are going to draw x squared. And if all you did was something like this, I would be really sad. You would be really sad. So because there are coordinates on here, let's make sure we're plotting points appropriately. Okay. So what would be one coordinate that I could draw on this graph for x squared?
One, one.
0.
1, 1. Good. What else? 2, 2. I would be really sad if you drew 2, 2 on the graph. I think you would be as well. Okay,
2, 4.
Yeah, we're drawing the function x squared. So 2 squared will give us 4, which would be here. Good. Ooh, 1/2 and 1/4. Yes, indeed. 1/2 squared is 1/4. That would be right here. And there's one other point that's like super nice that maybe we should draw.
0, 0.
Yeah, 0, 0 is a good one. Okay. All right. And I don't know about 1.5, but maybe let's square that right now. Another way of writing 1.5 is 3/2. So if I square that, I get 9/4, which is 1.0, which is 2.25, right? So 2.25 might be a good point to draw there. So 2.25, perfect. Okay. So on that Desmos activity, pretty much everything that you saw, oh, so close, showed you the actual function, right? Like it drew the function for you. And I think that's one of the things that we didn't really see in the last example that might have been hard for us to imagine, right? So here's the function, but let's see what it's asking us for. It's asking us to approximate the area using LRAM with n equals 4. And so they want us to take this piece down here, sort of where the base of the rectangle would be, and to go ahead and cut that into 4 different places, 4 different pieces, okay? And so if we were to find the base of each rectangle, we could do b minus a over n. In this case, we have 2 minus 0 over 4. which will give us 2/4, which will give us 1/2. Right? And so the base of each rectangle should be 1/2. Great question. Where did that 2 come from? Anybody got some eagle eyes, can see where we got that 2 from? How did we know that was the B though? You're right. You're very correct. 2 is our B, but how did we know that from our question? Yeah, it is sort of the end of the graph, but let's go back into the notation here for a moment. Turns out this bottom number is our A. It's telling us where we're going to start. And this top number is our B, and it's telling us where we're supposed to end. All right. Yeah, so the way we read this, right, is we're saying, let's look at the graph of x squared. The integral part means find the area under x squared. And where do you want me to find the area from? I want you to find the area from 0 to 2. Okay. And so when we look at our graph, it was almost hidden because I took a screenshot of an XY coordinate that would literally fit exactly what we wanted to do, right? So I sort of took some of that thinking out there, which is why your question is so great. Why would I choose my x-axis to be from 0 to 2? Well, because 0 is my A, my bottom number, and 2 is my top number or my B value. Okay, so thanks for making that explicit. So we've got our base as 1/2. And I'm wondering if you can, using function notation, all right, tell me which, what the values are for the heights of the 4 rectangles. All right, so don't give me a number, but say like f of something. What would the height of the, let's start with the first rectangle. What would the height of the first rectangle be? Ooh, all right. So trick question again. If I think about these 4 intervals right here, yeah, the left approximation means I start at f of 0. Okay. And if I think back to the table, I'm going to use the first 4, but not the last one for LRAM. And so if we draw in our rectangles, that might be helpful. Our first one is like a flat one. Then we have this one. Then we have this one. Then we have this one. All right. And this is an increasing function, or it has a positive slope. And so we can see that this is definitely going to be lower than the number we want. Okay. And so if we were to write this out in terms of our function notation, we would, as Sophia said, we would say f of 0, f of 0.5, f of 1, f of 1.5, okay? And to find our LRAM, we're going to say that it is the base times the sum of each of these values. And so f of 0 would be the first one plus f of 0.5 plus f of 1 plus f of 1.5. Okay, so that's like the function notation, but let's actually get a number this time because I think sometimes it's actually harder when we leave the number out of it. So what do we get for f of 0? Well, we get 0. F of 0.5 is 1/4. F of 1 is 1, and f of 1.5 is 9/4. So 9/4 plus 1/4 is 10/4, and then 14/4. So we have 1/2 times 14/4. Let's see, what does that give us? 7/4. Okay. So this says that the area that we approximate here is 7/4. That's the area of these 4 green rectangles. Okay. So let me pause here for a moment. Does that make sense to folks that we have drawn the function, we found our starting and ending point, we're able to cut these into equally based sizes, and then since we're using LRAM, we chose all of the left corners where that meant. And then we were able to find the area of the green rectangles. All right, any questions here right now? All right. Now, I'm going to ask a question that maybe for those of you who have taken calculus before can help me with, okay? So let's say that your teacher gave you this problem. Does anybody remember what you would do? Okay, and so what is the reverse derivative of x squared? Or the antiderivative of x squared? Good, okay. So we would write like 1/3 x cubed and then 2 and 0. Okay, what would we do with the 2 and the 0? All right, anybody else out there who's maybe taken calculus before? Like some folks have, you know, seen it in high school or maybe.
Yeah, that the bar means evaluated at those numbers, right?
And do you remember which order we put them in?
You subtract the lower function from the upper function. So
Yeah, so we would have like 1/3 2 cubed minus 1/3 times 0 cubed. And so this would be like the b value. This would be like the a value. You plug those into the function. Okay. And let's do a little bit of computation. So 2 cubed is going to give me 8, not 6, right? And so 8 times 1/3 will give me 8/3. And then this whole second chunk will become 0. And so we get 8/3. Okay. Now, I don't usually like to turn things into decimals, especially with thirds, because it's not very accurate. There's always like a repeating decimal, but can we take 8/3, turn it into a decimal just to see what we get? .6 repeating. Okay, so 2.6 repeating. Okay, so here's what all of this means. And we'll talk about this again tomorrow. So for those of you who have not seen calculus before, it's okay that you're like, I don't know what's going on right now. But if you have seen calculus before and you've been through this process, and it's just been a process where you find a number at the end and you're like, I don't even know. This number, here's what that means. This 2.6 repeating is if you found the area underneath this curve, between the curve and the x-axis, and you did like a bazillion rectangles, so it was exact, the area would be 2.6 repeating. Okay, so, yep, it's all about area. Literally, like the whole second half of calculus is all about area. Okay, so we said the exact is 2.6 repeating. Now, I left this as a fraction down here, 7/4, but let's turn 7/4 into a decimal. Okay, so 7/4 as a decimal, what is that? 1.75. Yeah, okay, yeah, so 1.75. So here's what we just did. Okay, we said, instead of finding this area using algebra and calculus, let's just use some geometry. Let's cut it up into some rectangles and we're going to find an area. And earlier, you all told me that something that looks like this with a positive slope, LRAM, is an underestimate. And check this out. The exact area is 2.6. But when we used the left approximation method, we got a number that was smaller than the actual area. Because we're missing all those little pieces, right? Like these red sort of curvy triangle things don't get counted when we do LRAM. So we should get a number that is smaller than what we're going to find out tomorrow is the exact value. Okay. So I hope this gives you a little bit of perspective in terms of like what we're actually trying to find. All right, so it is partially a process, but sometimes in really complicated functions, what we just did up here is too hard to do by hand. And so if we use a computer program and do an approximation where we can make it do like a million little rectangles, we'll actually get so close that it's good enough. All right, so that's kind of the cool part to it. All right, so we're going to take a look at this same function, so x squared, but in part 2, we're going to look at the right rectangular approximation. Okay, so if we know that the function looks like this, do you expect that the right approximation will be an overestimate, an underestimate, or it'll be like perfectly perfect? Yeah, it's going to be an overestimate, which means that at the end, when we get a number, it should be bigger than 2.6. All right, so that's sort of a clue how we know we're going to be right when we get a number that's going to be bigger than 2.6. Okay, so let me draw the picture. And as I'm drawing the picture again, if you want, you can start finding the heights of the rectangles for the RRAM. I had to hold my breath that time and it went better, so that's good. Okay, so we've cut this into 4 rectangles. All right, the base, that part is not going to change. I'm going to cheat. I'm going to copy and paste. All right, the base, that's not going to change. How can I modify the height? Good. I'm going to start at 0.5 and then 1, 1.5, and 2. And if I think about what that looks like on the diagram, that might be something like this, this. And so we can see that these pink rectangles are definitely taller than the function. And so when we find our area, it should be bigger than 2.6. Okay, so let's go ahead and change these values as well. We're going to change those. It'll give us a different number. So we've got 0.5, 1, 1.5, and 2. So let's see, what does that give us? 1/4 plus 1 plus 9/4 plus 2 squared is 4. Okay. So let's see, we've got 10/4 plus 5/4 or 5. So 10/4 plus 20/4 will give us 30/4, which should be 15/4. Let's turn 15/4 into a decimal. And I think we get, yeah, not quite 4, 3.75. Okay, so
I have a question
yeah, go ahead.
about base in this case.
Yeah.
Is it not is 1 because we have an n equals to 2?
Oh, okay, yeah. So it would be if we're 2. I think I got a little off track. I wanted us to try it again with 4, just so we could compare the values, because someone had brought up like, what are we actually finding here? So you're right, though. If it was 2, it would be 1.
Okay.
Okay, cool. Thank you. Sorry, I was so sidetracked by like these good questions that we were asking that I then just changed what we had here, which is a lot easier to hide when you don't have your notes already printed out. So, but I wanted us to actually compare these, right? Because we know that the pink ones are going to be above, right? The blue curve, like we have so much extra to count. And it turns out 3.75 is bigger than 2.6. And so that's why when we do the right approximation, it's going to be an overestimate of the exact area. Okay. So aside from the n equals 2 and 4 mix up, how are we feeling about what we see here on the screen? Better than before, worse than before, no change? So I think where we can sort of finish up with this section is let's try drawing the last one. Okay. We're going to do the MRAM one. We will not do the trapezoidal one, but we'll do the MRAM one just to kind of close out this section. Okay. And so what I'm going to do real quick is I'm going to go ahead and draw the function again. All right. Now this time I'm actually going to read what I typed, which is that this time we want n equals to 8. Okay. And so I'm wondering if you can tell me, based on what we have in our picture here, how big is the base for each rectangle? Good, good, good. Okay, so we can use that b minus a over n, which is 2 minus 0 over 8, which is 2/8, or better seen as 1/4. Okay. And so I'm going to go ahead along the x-axis right now and just draw the dividers that will divide this into our 8 rectangles. Okay. So I've drawn my 8 rectangles. Now, do we think that we're going to get a better estimate or a worse estimate than when we did the questions on the previous page? Yeah, why do we think it might be better? Yeah, for one thing, we're going to be taking the middle of each rectangle, right? And so middle tends to be sort of a nice balance between an over and an underestimate. But what else would make this better than our previous pictures? Yeah, higher n value, right? And so on Desmos, we were able to say, I want you to draw 1,000 rectangles. And Desmos was like, okay, I'll do 1,000 rectangles for you, no problem. But we're not going to sit and draw 1,000 rectangles, right? And so I think that like just seeing that the more we draw, the more accurate each one will be is a really good place to start, okay? Now, how would I find the heights? All right. So in particular, what is the height in function notation of the first rectangle? Okay, so let's maybe see, where is this first rectangle? It's kind of a short rectangle, but that's okay. So our first rectangle goes between 0 and I didn't label this, but I have 0.5 over here. So this would be 0.25, right? And so if we have 0 and 0.25, yeah, we don't want the left one. We don't want the right one. We want the one in the middle. All right, so the height of the first rectangle is f of 1/8. Okay. What is the height of this second rectangle? The one that is sandwiched between 1/4 and 1/2 in terms of the x values. Yeah. So this would correspond to that x value. F of 3/8 would correspond to this x value. And we should have a total of 8 y values. F of 5/8, F of 7/8. All of those, that'll be this one and this one. It's a little bit harder to draw when they're so short, but here would be like 1. And we can see, just as Luca was saying, that we have a little bit of it that is over the curve, but then we also have a little bit that's under the curve. And so therefore it might actually balance out quite nicely. Okay. We could keep going and we should end up with f of, let's see, 15/8 as the last one. okay? Now, if I tried to square each one of those, that would give me a lot of decimals. So that's another reason that we're sort of leaving it in function notation, because it's more about where we're finding them and how we're finding them than what the actual number is, okay? So we've got our LRAM, we've got our RRAM, we've got our MRAM, different kinds of approximations, okay? And they all compare to what we're going to be talking about in 5.2, which is this thing up here. And just to put a name on it, this is called a definite integral. Okay, so I did use that language over here, but I want to be really explicit that this actual like expression with the symbol, the dx, the function in between, and the numbers on the top and bottom, that is what we mean when we say definite integral. Okay. All right. So folks, if you're curious about the actual value, all right, and you have some time and patience to find all these y values and go ahead and multiply them out and or add the heights together, multiply by the base, my guess is that you're going to get a number much closer to 2.6 repeating. Okay, so if you want to show that to yourself on your own time, that could be a good exercise to think about, like how much closer you can get just by doubling the number of rectangles, or maybe even choosing that MRAM instead of an LRAM or RRAM. Okay. All right, so we're going to go ahead and stop this recording here.